Hi everyone, I'm Susrutha, and I'm a machine learning engineer at Stitchfix. I'm part of the recommender systems team here, and so today I'm going to talk about how we evolved our model training architecture to utilize multiple. So I'll start with a brief overview of our company and the motivation for this work. And then I'll focus on the technical details of how we can do data parallel distributed model training. And then I'll end with how we productionize this approach and share some learnings that came out of this work. I'm hoping this is useful for the audience here to deploy their own distributed model training in-house using open source tools. Yeah, so Stitch Fix is a personal styling company. So shopping can be overwhelming, right? We have to spend hours trying to find the right color, right fit, right style, and we have to do it again and again with new brands. Stitch Fix was founded in 2011 to solve these problems by personalizing the recommendations that we show to each of our users. And how do we do this? This is what a typical client journey looks like. When we have a new user, we ask them to create a style profile, which is where they provide some information about what kind of styles they like, what are their dimensions, what is their price point, what brands they like. And based on this information, they order a fix. A fix is typically a box of 5 items that we send them based on what we think they will like. Once the user receives these items, they can keep what they like, return what they don't like. But as part of checkout, we ask for feedback on all the items that they did keep and return. So as you can see, there are multiple touch points where we are collecting data from each of our users from the very beginning of their journey with us. And we use this data in our algorithms to optimize what is being shown to our stylists who are actually picking each item that goes into a fix for our users. So let's dive into what kind of data that we are getting from our users. So we gather client data for each user. We collect typically what styles they like, what is their price point, what kind of occasion they are looking for. Do they usually wear business wear or do they wear casual wear? On the other side, we also collect data for the merchandise that we are selling, like what is the material of the clothing item, what's the length, what's the sleeve opening, all the dimensions. We obviously have feedback data because every time they check out, we request for feedback on what items they liked and didn't like. And we also have an experience called Style Shuffle, which is where users can play. It's gamified, where you can look at different items that appear in the app, and you can give it a thumbs up or thumbs down. In the background, there's a machine learning model that's learning about both you as well as the item that is being shown, that this is what the style is about. And we have blog posts published too, if you want to learn more about that model. So one of the foundational models that we build using this data is the probability of sale model, which I'm going to focus on today. Or internally at Stitch Fix, we call it sale model, that estimates how likely it is that a client is going to buy any given item. So it's actually very simple. So for each client and item combination, we predict what's the probability that a user is going to keep it, if it's in a fix or they're going to buy it. And our goal is to make this estimate as accurate as possible because these scores are used across the company that power different personalized experiences for our users. Let's look at the model workflow now. The model workflow starts by getting all this data from our source tables. We generate our training data. Then there's a pre-processing step that happens before the model training starts. And this is intentional, that the pre-processing happens as its own separate task, because most of our pre-processing is CPU compute heavy, where we do some transformations and any cleaning that is required, all that is CPU intensive, whereas model training is all GPU intensive. So separating these two tasks helped us both reduce costs and keep the code a little cleaner so that it's not everything jumbled into one big job. And once the model is trained, We have both batch jobs, post-processing batch jobs that are triggered that use these features codes, both in client experiences as well as downstream other models. So there are other models that consume these cores and optimize for other experiences. And we also deploy a new model artifact. Every time the model is trained, we have some checks and balances in place to make sure that the model performance is at par with what we expect it to be. And if it is at par, then we deploy this for online inference. And the model itself is based on a GRU, Gated Recurrent Unit, with a temporally masked encoder called Client Time Series Model. And we've published papers and blogs about it, so you can read about it if you're curious on Stitch Fix's blog. So originally, when this model was written, we wrote the code using PyTorch, and it was running on one GPU. And we soon realized that this became a bottleneck in our development iteration as we expanded our business. So as we got into other product avenues for our clients, we collected more data, but we were not able to use all the data that we had. So for instance, for each client, in addition to like the style profile that we set up at the beginning and style shuffle ratings that I talked about, we also have text feedback. Our clients can request very specific items that they want to get in a fix. So we've had clients that say, hey, I'm going on a vacation to Hawaii. I need something for Hawaii. And they could be from New York, where it's cold. So we have valuable information available in this text data that we want to incorporate. We also get clickstream data from our mobile app, as well as our website, where users can click on items, they can say what they like, and this is valuable information. So all this information kept growing as we grew as a company. And on the item side, in addition to item specifications like color, dimensions, etc., we also have latent style embeddings that we are learning using the style shuffle interface. So we are learning what the latent style is for each item that we are selling that we want to incorporate in our model. And beyond that, we also have image embeddings. Because we have so many images for each item that we want to sell, we can also learn from the image itself that this is what the item is about and what's the right fit for that item, given the clients that we have. So as we expanded, the volume of training data grew beyond what could fit on one GPU. So in order to tackle this problem, we decided to evolve our training architecture to train on multiple GPUs. And there are two primary ways to do this. Typically, if you see what others are doing, it would be data parallelism versus model parallelism. So in data parallelism, we have one model that is small enough to fit on each GPU. What we are distributing is data. Because our data itself is so much that it cannot fit on one GPU. We use the same model that is on each GPU, but our data is distributed. Whereas in model parallelism, we distribute the model itself. So let's say you have a model that has 10 layers. We put 5 layers on one GPU and then 5 layers on the other. So the operation happens sequentially, where the 5 layers are computed first, and then the next GPU, the other 5 layers are computed. So in this talk, I'm going to focus on data parallelism because that is the problem we had. Our model was like small enough to fit on each GPU. It was the data that couldn't fit. Okay, so let's go into the details of data parallel distributed model training. So within data parallel distributed model training, there are two methods that are popular using PyTorch. One is called data parallel and the other is distributed data parallel, and then I'll go into the details of design and implementation. So let's start with data parallel. So let's take the scenario where we have two GPUs that we want to use for training our model. One of the GPUs is allocated as the main GPU that's going to do a lot of the synchronization work. So we start by initializing that model, our model on that GPU. And then right before a forward pass operation happens, we copy it over to this GPU and as well as all the other GPUs that we have available. In the next step, where we have a mini batch, let's say we have a mini batch of 1,000 data points that we want to use for training. Because we have two GPUs, This mini batch of 1000 is going to get split into 2 of 500 each, so half a batch goes to each GPU. Each GPU does its own forward pass using that model copy. We calculate output, we do the backpropagation, we compute gradients, and in the next step, the gradients computed are all accumulated onto the main GPU. So it's the main GPU that's actually computing what's the weights that should be updated in the model, and the cycle repeats. Once we have updated weights for the model, this new model is copied over again to all the other GPU. Forward pass happens on each GPU separately, gradients are computed separately, but then all gradients are again accumulated into the main GPU. This is how the operation happens for data parallel. So there are some pros and cons to this approach. The pro is that it's relatively easy to test. With a few lines of code, you can try this as long as you have access to a machine with multiple GPUs. It's very easy to test. And you can test it on a single instance with multiple GPUs. But there are some significant cons to this approach. The model needs to be broadcasted for every forward pass. And if your model is huge or like even of a reasonable size, this adds a lot of latency and takes away from the benefit you get from parallelization. The entire process is also orchestrated as a single process with multi-threading. So there's only one process that's splitting the batch, orchestrating forward pass on each GPU, and then accumulating gradients. Because of Python's GIL contention, you really don't get a lot of benefit because of the way this is orchestrated. And we also cannot expand beyond a single machine. Like we are limited to just one machine with multiple GPUs. If as a growing company, we want to use more and more data in the future, so this would limit us from expanding our training architecture in the near future. So now let's talk about distributed data parallel, which is what we did use at Stitch Fix. The way this works is, let's say we have 2 GPUs in our example again. We initialize the model on each GPU separately, and the forward pass happens same as data parallel. Each GPU does its forward pass, gradients are computed to backprop, and now there's a synchronization process where each GPU is broadcasting its gradients to all other GPUs that are available, and then each GPU is also responsible for receiving its gradients. So the exchange of information is happening across all GPUs. At the end of this exchange, each GPU has all the gradients that were computed across all GPUs, and we do just an average of that separately and then update the model within each GPU separately. The benefit of this architecture is that we only have one synchronization operation. There's no model copy, so it's super fast. There's a separate process that does the synchronization outside of the main training job. And each GPU can run its own process, can maintain its own memory, can maintain its own copy of the model, and it's very easy to scale across GPUs across multiple environments. The one con with this approach is that it does take some additional setup. It does take some understanding of multiprocessing, how device placement works. We have to make sure that the model, all the tensors are on the right device. Otherwise, you'll see an error saying, hey, my tensors are not on the right device. So it does take some initial setup. But even though it requires some initial setup, the benefits of this approach outweighed the cons of distributed data parallel. So this is what we ended up productionizing at Stitch Fix. So going into the journey of how we productionized it, the first version of DDP that we productionized utilized multiple GPUs on a single instance. We, for example, the G5.48x large instance from AWS that has 8 GPUs. So we utilize that instance. But in the future, if we do grow, we can set up a cluster of GPUs and use the same code with some change in the setup and use GPUs across multiple instances. We also use PyTorch Lightning Framework to reduce the amount of multiprocessing code that we have to maintain. And that significantly reduced the maintenance overhead. We can write device agnostic code. We don't have to make sure that all the tensors are on the right device. That is sort of done by Lightning in the background, and that helped us reduce the maintenance load. So we did try increasing the number of GPUs to test how much efficiency we can get just by parallelizing. And we saw that the communication cost did go up as we scaled from 1 to 2 to 4 to 6 to 8 in this graph. The percentage of time spent in just communication did increase overall. In spite of the increase, this did solve a lot of our problems that we had since we wanted to use all the data that we had and train in a reasonable amount of time. We did end up adopting it initially with 2 GPUs, but we can expand it to 4 and 6 as we get more data. We also use TensorBoard for monitoring our model metrics and gradients. And because of the way DDP does batch computations, so each GPU is running its own process, and each GPU gets its own batch. You are training on 2 different mini batches, or like n different mini batches if you have n GPUs. So if you track the loss on TensorBoard, you may see the loss slightly different for each GPU, but once you smooth it out, it's sort of all declines in the same way, that like the trend is similar, where the loss is reduced over time. But you may see small fluctuations because each process is using its own different subset of data. Yeah, so in conclusion, we, using DDP with Pytorch Lightning, significantly minimized our overhead to maintain multi-processing code, and it also enabled us to scale up our GPUs. We've been doing this for different experiments that we've been running. We've experimented with using multiple GPUs. Maybe one thing to note is that scaling up GPUs does mean your effective batch size is changing. Because of the way DDP does averaging of gradients, if you, instead of using 1 GPU, if you use 2 GPUs, that essentially means you've doubled your batch size. So because batch size is an important hyperparameter, this would typically require tuning of hyperparameters that you have, like maybe training it for longer or changing other hyperparameters that you have in your model. So you may have to do that. And after making all these changes, we ran a do no harm experiment to make sure that this does not negatively impact any of our online business metrics. And once it was successful, we adapted it fully in production earlier this year. So overall, this approach helped us to use more data that we have, build better models, and deliver more personalized experiences for our clients.
Thank you so much, Susrutha. Thank you so much, Susrutha. We have time for a few questions. Please raise your hand if you have any.
So what sort of effects did being able to use the entire data set have on the training loss at the end of the experiments?
So we did see successful experiments because we were able to use all the data that we had. Previously, we had to sample our data because we were limited to 1 GPU. We've run several experiments since we moved to multiple GPUs, where we just used all the data that we had, used more text data, we used more clicks, and all of them incrementally gave us like statistically significant wins for each experiment.
Thank you.
Yeah, that's a great question. So this particular approach does not solve that specific problem. I think that's a problem that we are aware of in general in our Rexus stack. So this model is responsible for predicting probability that someone's going to buy an item. But this is not the only model that we have at Stitch Fix. We have several models downstream that make sure that we have enough diversity, enough variety in the items that we are sending out. So they take care of ensuring that.
Hello. Does the distributed data parallel way of doing the multi-GPU parallelism work well for models other than transformers?
Yes, our model is sort of like a transformer. We use an encoder we don't do individual event sequence. Yeah, so we batch events. We batch a few events together. That is where the temporally masked encoder comes into place in order to improve the efficiency. But if we remove the batching, we could use the individual events, and that would be a transformer model. So this actually works for a transformer.
Thank you so much, everyone. We are now taking a break for lunch. Oh, there is the last question. Sorry.
Yeah, I was wondering if there was a model calibration step, since I'm assuming piece sale touches revenue.
Yes.
Does it happen like outside of the diagram you showed earlier?
By model calibration, do you mean probability calibration?
Probability calibration.
Yeah, that happens outside by other downstream models that we
Okay.
have.
Thank you.
Hi, I'm just curious to know if your model parallelism is also similar to this in terms of actual GPU orchestration?
It's not, because the model itself has to be split across multiple GPUs. It's entirely different, I would say. We have not used it.